Hello, I hope you're doing well. My name is Giovanni, and in today's video, I'll walk you through how to implement a multi-layer perceptron for multi-label classification. I know that this topic is kind of old, but with all the buzz around AI, terms like generative AI and transformers being thrown around constantly, I think it's important for those who are truly interested in the field to also build a solid understanding of the basics. On this channel, I'm launching a mini series of short tutorials covering key topics in AI, physics, and finance. So if there's a topic you would like to see, feel free to leave a suggestion in the comments, and if I'm making mistakes, don't hesitate to correct me down below. Alright, let's jump in. Okay, so now, before heading into the tutorial where I'm going to show how to implement a multi-layer perceptron, how to train it using Apple's MLX AI accelerator, I'm going to give a short introduction to the theory behind multi-layer perceptrons. Please note that my presentation is going to be fairly concise, and I plan to make a more comprehensive video on each of the components that I'm going to go over in this presentation. So, to get started, a multi-layer perceptron is just a type of artificial neural network that consists of multiple layers, including an input layer, one or more hidden layers, and an output layer. So each node in a layer is connected to all other nodes in the next layer. And this allows for the learning of complex relationships in data through weighted connections and activation functions. Before the rise of more advanced neural architectures like convolutional neural networks, or more recently the transformer, the multi-layer perceptron was the basis for all of this, and it was the go-to model for any sort of task, because it was one of the earliest forms of deep learning. In fact, I believe it dates somewhat until the 60s through the Rosenblatt perceptron. And these MLPs laid the foundation for our modern understanding of neural networks. However, despite their simplicity, they're very powerful, since they serve as a universal function approximator and remain highly relevant for tasks like tabular data, basic image recognition, and they also serve as building blocks for larger models. In fact, I believe the vanilla transformer architecture has a fully connected linear layer after the attention blocks. So understanding MLPs is crucial for grasping the core concepts and principles of deep learning, such as backpropagation, nonlinearity, and weight optimization. This applies across all other modern architectures. So the basic architecture of a multi-layer perceptron includes an input layer, which receives the data. In this case, it would be image data. In further videos, I'll go over why the multi-layer perceptron is not the ideal architecture for this task, and it mainly deals with the fact that images are comprised of pixels. So an array of 3 numbers corresponding to red, green, or blue. And the values of these pixels are somewhat dependent on each other. We say that there is a spatial dependence on it. If it's a video, then we have a spatial temporal dependence on it. And because multi-layer perceptrons are inherently linear layers, in order to feed an image into one of these architectures, we first have to do something called flattening, which involves stacking the individual pixel values in a single vector. We can see that this is non-optimal because it breaks any sort of causality and locality. And for this reason, in further videos, we're going to explore more sophisticated architectures that solve this problem, specifically the convolutional neural network, and more recently the vision transformer. But in this architecture, once we feed in the data to the input layer, what happens is that it is passed through a hidden layer. But before it is passed, each individual data point for each individual neuron would be evaluated with a nonlinear activation function. And the arrangement of these layers allows MLPs to model complex relationships and visual data effectively, but not too effectively as compared to weight sharing in kernels. Okay, so how do we train these neural networks? The first step is to prepare the data. And this is because in this case, images might come in all sorts of shapes. So we have to bring down and normalize them to a desired dimensionality. The MNIST dataset, I believe it's 28 by 28. We could upscale or downsample, but I'll keep it as a dimension as it is downloaded. And effectively preparing the data is crucial for training MLPs, specifically in image classification. And this involves, the collection of diverse data sets, normalizing pixel values, and augmenting data through techniques such as rotation and scaling. In further videos, we're also going to see how we can go around this using newer types of architecture, specifically equivariant neural networks, which encode these aspects into the architecture itself. So properly prepared data ensures that the neural network receives input that enhances its ability to learn different features and patterns that are relevant for accurate classification. So what makes all this work, right? Because if we look at the architecture, we're just essentially passing values forward. So how does the architecture learn how to optimize these weights so that the predictions actually match the labels on our data? So that is solved using an algorithm called backpropagation, and this is really what serves as the workhorse for any modern deep learning architecture. So backpropagation deserves a video of its own, but in this video I'm going to provide a high-level description of it. So the backpropagation algorithm is essential for training multi-layer perceptrons, and it involves a forward pass where the inputs are processed to generate an output, followed by a backward pass that computes the gradient of the loss function with respect to each weight. This allows the model to update weights iteratively using optimization techniques, so minimizing the error and improving the performance. And in general, how this algorithm works is that first in our neural network, all weights and biases are initialized with random values. Then we, for each epoch, and an epoch refers to passing all of our data sequentially through our neural network. And for each training example, for example, the image, either a dog or a cat, and the label, whether dog or cat. For each of this training example, we do the forward pass, which sets the input layer activations equal to the input. And then for each layer, we compute the pre-activation and apply the activation function. The backward pass, we compute the error and then backpropagate the error through the weights. So that's just a high-level description. In future videos, I'll go over the mathematics behind this algorithm and perhaps how to derive it. It's fairly interesting. And the last component in this ML training pipeline is evaluating the performance. So we ask the question, how good does it perform compared to test examples? And this is done once we've trained our MLP, and it's important to understand how it performs and how to identify undesired things such as overfitting. In this step, some commonly used key metrics include precision, recall, F1 score, Hamming loss, but for our simple example, we're simply going to use the accuracy. Alright, now let's head into the tutorial. So now we are in the tutorial where I show how to implement the multi-layer perceptron As I stated before, we're going to be using Apple's MLX AI accelerator. Essentially, it's a framework that allows you to make use of the GPU that's inherent in your Mac or MacBook to just train neural networks faster. I'll make a future video explaining how this works. But if you have a Windows system, feel free to refer to the GitHub in the link in the description, because I put essentially what I show in this notebook, but on using PyTorch and CUDA. Okay, so how do we implement our MLP? So first, if you don't have it installed, make sure to install MLX, and you do that by simply typing pip install MLX, and I already have it. But other than that, you can go ahead and check the platform, and ideally it should say ARM. That indicates that the computations are occurring in your M1 processor. Then you go ahead and import the dependencies, ml.core, mlx.in, which is the analog of torch.in if you have experience implementing neural nets, and optimizers, which contains several ones such as Atom, SGD, etc., and then NumPy. And then when it comes time to declaring our multi-layer perceptron, we have 4 inputs, 4 hyperparameters: the number of layers, the dimension of our hidden layers, the dimension of our input data, and the output dimension. In the case of the MNIST dataset, we have output dimension 10 because we have digits from 0 to 9. We then go ahead and define and declare them as properties of our object, and then we have layer sizes. This creates a array that contains the dimensions of each of our layers. So it's going to, the first entry is going to be our input dimension, the second entry is going to be the dimension of our hidden layer repeated times the number of layers we have, and then we're going to have the output dimension. So if we have, for example, input dimension 10 and then a hidden dimension 20 and 5 such layers, then we're going to have a 10 followed by the next 4 entries, or the next 5 entries, which are going to be 20s, and then our output dimension, which is 10 again. Then we have layers, which is simply a list, and we're calling the this nn.linear from our neural network module from MLX. And what this creates are densely connected, fully connected layers, where the input dimension is 10. It increases sequentially up to the output of, in this case, 10 again. And then we have this def call, which is the method that it's called once we instantiate our MLP. Then we implement this helper function to declare the loss, and as we can see, it's just the cross entropy. I will make a future video explaining how the different loss functions differ from one another. And then we have our evaluation function, which is going to help when we are testing the accuracy of our model. And here I simply declare the hyperparameters, and I write some methods to explore our dataset. We have 2 layers, hidden dimension. I chose 64. The number of classes is again 10. Batch size 128, and 100 epochs is more than enough for this simple use case. And then to import the data, you just go ahead and call import MNIST. If you haven't done so already, please clone the repository linked through GitHub in the description, because here I have a script called MNIST.py, which automates the retrieval and formatting of the data. If you're interested in seeing how that happens, feel free to parse through the script, but here I decided not to include details to avoid deviating from the core topic. And then visualizing the data, here I simply implement a method that iterates over the first 9 entries of our training images, and then just shows them. And as we can see, they're just handwritten digits. The next step is to implement our data loader, and if you're using a framework such as PyTorch or TensorFlow, it already comes preloaded with some data loaders, but here I show how to do it. And essentially, you simply first have to create a permutation array, which contains random indices in a range, in this case, between 0 to the size of our output. And then for each element in this, in the range 0 to the dimensionality of our output and steps of our batch size, we create an IDs, which is simply a list with random indices in our permutation array, and then we just return our X, which is our training images that correspond to the IDs, and then our labels that correspond to those particular images. The next step is just instantiating the model and implementing the training loop. So for the model, I call the method that I previously implemented, the class that I previously implemented, and just define or declare the hyperparameters. Since MX is something called lazy evaluations, we have to use explicitly mx.eval to initialize the model parameters. And then we have this helper function value in grad, which returns the loss, which equips our model with a particular loss function. And the optimizer is just a stochastic gradient descent with our learning rate of 1 times 10 to the minus 2. And then we have this losses array, which is going to store the loss at each particular epoch to plot the loss as a function of epoch. And then for each epoch, we simply fetch a batch of data, and then we run it through our loss function and evaluation function, and we store the loss for a particular epoch, and then sum it to our epoch loss. And then we update the weights using backpropagation, and we use mx.eval to explicitly evaluate our model parameters and the state of our optimizer. And then we just append the losses to the losses list. And then we just evaluate the accuracy using the eval function we defined earlier. And then we just print the epoch and then the accuracy. And as we can see here, I already trained it. It just takes in the order of a few seconds, but I can rerun it again just to make sure it works. Okay, we can see how the test accuracy is increasing over our epochs. And then just using the number of epochs we have and the losses list, I plot it, and ideally when you train any AI model, you should see a curve like this, exponentially decreasing. And then I just select some random integer and then fetch a test image with this random integer as an index and the label, and then I am just showing it, which is 4. And then I evaluate the model using the test image, and I read what the model outputs, and in this particular case that's 4, which agrees with our expected value. So yeah, so in this tutorial I showed how to implement a simple multi-layer perceptron for image classification in the MNIST dataset. It is worth noting that you would only want to use MLPs for these types of very simple datasets, because if you want to do image classification in more sophisticated images, say images with RGB colors or images with several features, you would want to use convolutional neural networks. So stay tuned, because in future videos I plan on discussing those architectures. And if you enjoy me using the MLX framework, feel free to comment. If not, I'll continue using it and keep on appending to the GitHub repository corresponding notebooks with the PyTorch / CUDA implementation. And yeah, I hope you enjoyed this video, and please feel free to subscribe, comment, and activate the notifications bell so that you don't miss out when I upload any new videos. And with that, thank you.